Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 12 on AAS and isosceles triangles. Well, you certainly know what isosceles triangles are, but probably don't know what AAS is. So let's get right into the lesson and explore it. All right, the AAS theorem. We now have the SSS, SAS, and ASA theorems to prove that two triangles are congruent. In this lesson, we will add another way to prove triangles are congruent, the angle-angle-side theorem. Angle-angle-side, not angle-side-angle, but angle-angle-side. So let's take a look at what that theorem says. If two angles and a side not between them in one triangle are congruent to two angles and a side not between them in another triangle, the two triangles are congruent. And as always, we should prove this theorem before we use it within proofs. All right, so it's interesting because, we had a theorem already that involved two pairs of congruent angles and one pair of congruent sides. This does as well, but there's a difference. And that's the first thing we're going to take a look at in exercise number 1. So let's take a look at that exercise. In the diagram shown below, angle A is congruent to angle D, angle B is congruent to angle E, and side AC is congruent to side DF. Letter A. Why can we not conclude that these two triangles are congruent by ASA? All right, well, pause the video now and see if you can answer why we cannot conclude that the triangles are congruent by the ASA congruence theorem. Well, it's pretty simple. To use the ASA congruence theorem, the side pair that you know is congruent has to be between the two pairs of congruent angles, right? It's got to be the included side. Now, that would be fine if we knew that AB was congruent to DE. So if we knew that AB and DE were congruent to each other, then we could use ASA. But because that side does not lie between the pair of congruent angles, we can't use ASA. So let's get that down. Because the pair of congruent sides does not lie between the pairs of congruent angles. Right. And that's important because you will have situations on tests, right, both probably that your teacher gives you and ones that you might see at the state level, where you'll have to be able to say, oh, which theorem can I use in this situation? And you want to make sure that in a situation like this, you don't think it's ASA, but you'll eventually know that you can use AAS. Now, we still haven't proved why AAS works, so let's take a look at letter B. Do a short partition proof to show that angle C is congruent to angle F. So I claim that we can prove right now that angle C is congruent to angle F without actually proving that the two triangles are congruent and using CP/CTC. All right, so let's do this one together. All right, so what's the first thing I might say about these triangles? Well, first, maybe I just write down my givens. Angle A is congruent to angle D, and angle B is congruent to angle E. All right, so that's simple enough, and that's just my given. All right, so I can also say that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees, right? We've proved that already, so we can use it. And the reason is the interior angles of a triangle total 180 degrees, or sum to 180 degrees, or something. Please don't use as your reason that a triangle is equal to 180 degrees. That's like saying a llama is equal to a peach. It doesn't make any sense. All right. We can also say that the measure of angle D plus the measure of angle E plus the measure of angle F is 180 degrees. And of course, the reason is going to be identical because the interior angles of a triangle total 180 degrees. All right. Now, since both of these two are equal to 180, it's obvious now that we can say that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to the measure of angle D plus the measure of angle E plus the measure of angle F, right? And that's just the substitution property, right? If they're both equal to 180 degrees, then they must be equal to each other. Now finally, right, we know the measure of angle A is equal to the measure of angle D, and the measure of angle B is equal to the measure of angle E, so we can subtract those from both sides of this equation, leaving us with the measure of angle F is equal to the measure of angle C, right? And that kind of makes sense, right? Just think about it. Forget about those two sides being equal. If I know that these two angles are equal to these two angles, then the third angle has to be equal, the third angles, sorry, have to be equal to each other because all the angles have to add up to 180, right? It makes sense. If these two added up to 100 and these two added up to 100, then both of those two angles would have to be equal to 80. They'd have to be equal to 80, right? So think about this, right? What can we now conclude, or sorry, why can we now conclude that triangle ABC is congruent to triangle DEF? Think about this for a moment, right? What we just saw was this scenario allows us to conclude this, right? So if we now know that if this is true, and then if this is true, why can we now conclude that those two triangles are congruent? Pause the video and see if you can take a shot at it. All right, well now with this scenario, we do have angle, side, angle, right? Angle congruent to an angle, side congruent to a side, angle congruent to an angle where that side is between the two included angles, so we can now conclude by ASA that the triangles are congruent. So in other words, let's break it down. Angle, angle, side, right? That theorem is a direct consequence of two things, angle, side, angle, and the fact that the three angles of a triangle, of any triangle, must sum to be 180 degrees. So angle, angle, side implies that angle, side, angle can be used to prove the two triangles are congruent. But that's great because now I can use angle, angle, side to prove that two triangles are congruent, and I don't have to go through every time and prove that the third angle of each of the triangles or the third angle pair is also congruent and use ASA. Now that I've done it, I can use angle, angle, side anytime it makes sense to do so. And let's take a look. Now that we've proven the angle, angle, side theorem, we can use it to prove that triangles that fit those conditions are congruent. Let's take a look at an example in exercise number 2. Given that segment AD bisects angle BDC and angle B is congruent to angle C, prove that side BC is congruent to side CD. All right, well, let's kind of lay this out together. Let's take a look. First, given AD bisects BDC, right, that is going to tell me that this angle, let me just do this really quick, that this angle is congruent to this angle, right? Bisectors divide an angle into two congruent angles. Now, we were also told, right, that angle B is congruent to angle C, so I can mark those two. Now, the final little piece, right, is the fact that these two triangles share side AD, right? That's that whole reflexive property thing. That means I'm going to be able to prove that triangle BAD is congruent to triangle CAD by angle, angle, side. Notice in this case, right, that the side is not between the two congruent angle pairs, right? It's not there, right? It's sort of outside of those. So I'll have to conclude that these two triangles are congruent based on angle, angle, side, and then I can conclude that BD is congruent to CD by CPCTC. What I'd like you to do is pause the video and see if you can fill out the proof. All right, let's do it. Simple enough. Step 1, segment AD bisects angle BDC, given. Let's get that second given down. Great, given. All right, we got it. Now, what's the first thing I want to do? I'm going to conclude that angle BDA is congruent to angle CDA, and that is, of course, because a bisector divides an angle into two congruent angles. Simple enough, right? Now I can say that AD is congruent to AD because of the reflexive property. All right. Now I can say that triangle ACD is congruent to triangle ABD by the angle-side congruence theorem. And finally, I can state that side BD is congruent to side CD because corresponding parts of congruent triangles are congruent. Every once in a while, I want to remind you what that means because you don't want to write down CTPTCDD, you know? You got to actually kind of get that right. All right, pause the video now and write down any of these steps that you need to. Okay, let's move on. And now let's talk about the second part of the lesson, right? Like the lesson was entitled AAS and Isosceles triangles. So, now that we have both the SAS and AAS theorems, we can prove two important properties that are regarding isosceles triangles, okay? And these are properties we've already kind of looked at, but now we're going to really formally prove them. Exercise number 3. Isosceles triangle ABC is shown below with AB congruent to CB as shown. We want to prove that the base angles of an isosceles triangle are congruent. So take a moment about this. Now, we looked at this and we actually proved this with rigid motions earlier in the course, but now we're going to do it with a Euclidean triangle proof, right? This idea that if we have an isosceles triangle, a triangle where two sides are congruent, then the angles that are opposite those two sides are also congruent. So somehow, we want to prove that angle A and angle C are congruent. Now, typically, if we're trying to prove two triangles are congruent, we actually need to prove two triangles are congruent and then use CPCTC. So let's take a look at how we're going to do that by beginning at letter A. Hand sketch, as best as you can, the angle bisector of angle B. Mark its intersection with segment AC as point D. This is known as an auxiliary line, a line added to a figure to help prove or understand something. This is certainly not the first time we've seen an auxiliary line. We actually saw one in the last lesson when we were trying to prove that, that exterior angles were the sum of the two remote interior angles, and here we go again. So what I want you to do is do the best job you can in trying to draw in the angle bisector of angle ABC, or angle B, whatever. Pause the video now and go ahead and do that. Now, I'd like to remind you of something that we talked about earlier in the course, which is that every angle has a unique bisector, okay? So the idea that I'm just going to randomly draw in the bisector of angle B on this diagram as an auxiliary line, or ray or segment or whatever, is completely okay. There's nothing wrong with doing that. So hopefully I can get it. There it is, right? So I've drawn in the angle bisector. I've even drawn in the two congruent angles with congruent angle symbols up there. We're good. Letter B, now prove that angle A is congruent to angle C. All right, well, let's do it. We want to now prove that angle A is congruent to angle C. I'd like you to pause the video now and think about your strategy and how you might now do this proof. Keep in mind, you now have two things that you know. One thing you know is that AB is congruent to BC, and the other thing that you know is that these two angles are congruent to each other, okay? Because you made them so by drawing in the angle bisector. All right, pause the video now and think about strategy, then we're going to come back and talk about it. Well, it's actually relatively simple, right? At this point, we know that AB and CB are congruent to each other, and we know that angle ABD and angle CBD are also congruent to one another, right? Finally, we also know that side BD is congruent to itself, and that will allow us to prove that triangle ABD and triangle CBD are congruent to each other by side angle side. Right? Side, angle, side, all right? And because we know those two triangles are congruent, we can now prove that angle A is congruent to angle C by CPCTC. I'd like you to pause the video one more time and see if you can write out the proof. All right, let's do it. Now again, the weirdest part of this proof is probably the idea that we can just draw in an angle bisector when there wasn't one there to begin with. And again, that's okay. Every angle has a unique bisector, so it's completely okay to draw it in and then use that auxiliary line to do the rest of the proof. Here we go. All right, BD bisects angle ABC. That's given. All right. 2, AB is congruent to CB. That is also given. Angle ABD is congruent to angle CBD, and that is, of course, because a bisector divides an angle into 2 congruent angles. Finally, BD is congruent to BD by the reflexive property. All right, that's all we need now to conclude that triangle ABD is congruent to triangle CBD by the side angle side congruence theorem, and that is now enough to say that angle A is congruent to angle C by CPCTC. And that is the classic way that you prove that angles in a triangle that lie across from congruent sides are themselves congruent. But it's a little tricky because you have to draw in that angle bisector. You have to draw in that auxiliary line, right? Literally, it means a helping line, right? Got to draw that in order to get the 2 triangles that you prove congruent. All right, pause the video now and write down anything that you need to about this proof. All right, let's keep going. Now, the other thing that we want to do is we want to prove a related theorem to our last one, which is that sides that are opposite congruent angles in a triangle must be congruent. So this is kind of like running what we did last time, but in reverse. This time I want to start with a triangle where I know that 2 angles are congruent, and then I can conclude based on that that the sides opposite are also congruent. So let's take a look at exercise number 4. Triangle ABC is shown below with angle A congruent to angle C. We want to prove that, in a given triangle, sides opposite congruent angles are congruent. Letter A, like the last exercise, hand sketch the angle bisector of B and label its intersection with AC as point D. All right, so I want to start exactly the way we did last time. Why don't you go ahead and hand sketch that angle bisector in and label that intersection point as point D. All right, here we go. As usual. Oh, apparently I did not actually put that one in. Fine. This time I will just hand sketch it in. Man, I don't know who did the graphics here, but okay. All right, now keep in mind again, just like before, because that is the angle bisector, I know that that angle and that angle are now congruent. Okay? So yet again, I want you to pause the video and think about your strategy. Now remember, your last line should be AB and CB are congruent to each other. So how are we going to get there? So just pause the video, think about your strategy. We'll come back, talk about the strategy, then we'll have you work on the proof, then we'll come back and talk about the proof. Pause the video now. All right, so, right, we know this angle is congruent to that one, right? That's our original given. We know this angle is congruent to that angle because we drew in the angle bisector, and just like before, we know that side BD is congruent to itself by the reflexive property. That now means that I can prove that triangle ABD and triangle CBD are congruent to each other by angle side, right? Now the side that we know is congruent is not between the 2 congruent angle pairs, yes? All right. So we can conclude that those 2 triangles are congruent by angle side, and that will then allow us to conclude that AB is congruent to CB by CPCTC. So pause the video now and see if you can get this whole proof written out. All right, let's do it. Here we go. BD bisects angle ABC, right? That's a given. Angle A is congruent to angle C. That's a given. Angle ABD is congruent to angle CBD. This seems a lot like the last problem. right? A bisector divides an angle into two congruent segments, and BD is congruent to BD by the reflexive property. So really, everything here is very similar to the last problem, with the big difference being instead of having like the two sides congruent in our given, we have the two base angles congruent. And now, also another big difference is we can now conclude that triangle ABD is congruent to triangle CBD, not by side angle side or angle side angle, but by the angle angle side congruence theorem, which, by the way, is why this is showing up in this lesson. All right, finally, we can conclude that AB is congruent to CB because corresponding parts of congruent triangles are congruent, CPCTC. All right. Now, both of these, by the way, both of these facts, the fact that angles across from congruent sides are congruent and sides across from congruent angles are congruent in a given triangle, both of those now are facts that we've proved, and so you can use those two facts in further proof. In fact, you will have to use those two facts in further proof, and we'll kind of see that as we move on. But let's do one last thing, right? So we can now be expected to use one of those two properties, especially the one that says that angles across from congruent sides are congruent, all right, in problems where we're just sort of trying to figure out measures of angles. So let's take a look at exercise number 5. In the diagram shown, BD is parallel to AC, segment BC is congruent to segment AC, and the measure of angle BAC is 74 degrees. We want to figure out the measure of angle DBC. All right, well, I'd like you to pause the video, play around with this problem, fill in any angles that you know, right? Think about principles that we have with both parallel lines and isosceles triangles, and see if you can work your way around to where you figure out what the measure of angle DBC is. All right, this is truly what I call a fill in the angle problem. And before we start filling in angles, I'm going to just highlight which angle we're trying to find. I think that's always exceptionally helpful to be like, all right, we need to figure out the measure of angle DBC. All right, that's the angle I want, right up there. Okay, now let's see what we know. We know that the measure of angle BAC is 74 degrees. That's right here. We also know that BC is congruent to AC. Now, as soon as two segment lengths are congruent to one another and they're two side lengths in a given triangle, then you've got an isosceles triangle. Now, this isosceles triangle is a little more challenging, right? Because it's sort of, if you will, sitting on one of its legs, okay? But that doesn't matter, right? The angles that are across from congruent sides have to be congruent, which means this angle must also be 74 degrees. Wow, that almost looks right. Anyway, that angle is supposed to be 74. Now that I look at it, it just doesn't look like a 74. I'm really, here we go. Okay, looks a little bit better. Anyway, these two angles have to be 74 degrees. Now you have a couple routes from here. All right, you could add the two 74s together. You'd get 148. You could then subtract 148 from 180, which would give you 32, and that would be this angle down here. And then DBC is an alternate interior angle to that one, and that would give you the angle there. Or you could say that this particular angle is supplementary to angle ABD, right? So you could do a 180 and subtract off 74 to give you all of this angle, and then subtract off another 74 to give you what remains. I kind of like getting in that like alternate interior angle, so I'm going to literally just do, 74 degrees plus 74 degrees. That's going to give me 148 degrees. I'm going to then do 180 degrees minus 148 degrees, which is going to give me 32 degrees. That's going to be right here. All right. And then this angle and this angle have to be congruent to each other because they're alternate interior angles. So I'm going to say the measure of angle DBC is 32 degrees. All right, and that's it. Okay? These types of problems where isosceles triangles end up just sort of showing up, right, in a larger diagram, it happens all the time in geometry. So if you have two sides in a triangle that are congruent, then the angles opposite of those two congruent sides are also the same measure. They're also congruent. Okay, let's wrap this up. Now, we saw a few different things in today's lesson, right? One of the things was a brand new way of proving two triangles are congruent, the angle-angle-side theorem, right? And the difference between that theorem and angle-side-angle, we went into in depth. Make sure you understand that. We then looked at two important ideas that sort of revolve around isosceles triangles. One, the idea that if you have a triangle where two sides are congruent, i.e. an isosceles triangle, then the angles opposite the two congruent sides have to be congruent. We then flipped that one sort of on its head and we said, look, if I have a triangle where two angles are congruent in that triangle, then the sides opposite of those two congruent angles also have to be congruent. Okay? And both of those two theorems will come up in proofs and algebraic problems like the last one that we saw. All right, for now I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.